Hello, everybody. Second day lecture. So yesterday we discussed a few elements, basic elements concerning aspects of flavor in the standard model, mostly at the level of how you can see the various elements that are going to be of interest for us in the next lectures coming up. Many parameters, hierarchy of scales, the fact that you do have CP validation embedded in the weak interactions, the fact that you can use neutral currents that are suppressed in the standard model as a way of getting some kind of quantum sensitivity to higher scales. So yeah, and to answer your question, there is some kind of background noise, Fabio, indeed. As if there was somebody with
Okay, so I hear you very, very faint, and I hear some background noise too. So let me check whether there is someone with a Julia. Wait, so Julia, I'll mute her.
Yeah. It seems that Julia was.
Okay, so was okay. We fixed it. Yeah, thank you.
Okay,
yeah, sorry.
That's no problem. Don't worry. That must be painful for you, actually, more than for us. Okay, so that's good now. Okay, so yes, so as I said, we discussed a few elements of flavor that are going to pop up again and again. But before discussing different aspects, mainly how we have handles on the CKM metrics on one side and the connection with CP validation, and then some intriguing aspects of rare decays that have been present recently, so-called anomalies. I thought that it was useful to spend a bit of time on aspects. So it's going to be a mixed handbag of aspects of theoretical tools for flavor. So I don't know up to which extent I will be able to cover everything today, but one thing which is clearly important for what we are discussing is everything related to effective Hamiltonian. Then the second question is how to tackle hadronic matrix elements. And if time allows, a junction between the two, which is the use of heavy quark effective theory. Because those are tools that are going to be very useful for us in the following. So I'm going to start with the general concept and ideas concerning the effective Hamiltonian. So actually, that's something that arises exactly both as something which is very interesting and also occurs for flavor. As I said, you've got many different scales into the game when you're discussing the physics of flavor, because in principle, you have things that are related to W and Z masses. Then, as we discuss, we have also the Higgs being present, Higgs physics, so anything related to the typical scale of electroweak symmetry breaking. And I put also in this the top. And so all this is going to be electroweak scales that are relevant because at short distances, we need those various degrees of freedom. But then, as we discussed already, we have to deal mostly with fermions that have a mass scale, which is much lower. So apart from the top, which has a very specific position in this landscape, then you have the big quark mass and then the charm quark mass. Then you've got the strange, obviously it's not to scale, I'm not trying even to do it. And then you've got U and D somewhere very close to zero. And the fact is that, okay, so probably I should just put this sign in order to tell you that actually there is quite a large range between those two. And then you see that this is going to be the region of interest for most of the for flavor studies, at least concerning the external states. We're going to look at the way that big quarks, charm quark are going to decay through the weak interaction or other things into lighter quarks and so on. So you've got this, and then you've got also another point which I've not mentioned, but which is quite obvious, is that actually somewhere here, there is a scale that makes life a bit more complicated. It's the typical scale of QCD. So the fact that when you go below some scale, typically a fraction of a GeV, then you have non-perturbative effects of QCD, of the strong interaction. So everything else that I've discussed, being the electromagnetic interaction or the weak interaction, you've got couplings involved that are small and for which you can hope to do some perturbative computation. Higher and higher orders will give you an increasing accuracy, at least in principle. But you do have troubles with the strong interaction, especially the fact that it's a theory which have this Landau pole, and then you have the coupling increasing when you decrease the energy of interest. And the problem is that when you think of a flavor process, it will involve all scales, the weak part, interactions occurring at the typical electroweak scale that I've mentioned before, but you've got also the strong interaction. And so this one is present everywhere. I mean, you do have also a part of the strong interaction that corresponds to exchanges of energetic gluons between the various components of your mesons, of your hadrons. But you do have also a part that you cannot analyze in those terms, and that remains purely non-perturbative. And on top of that, I've not mentioned it, but somewhere you've got maybe new physics, and then that's also some energy range, which is not clear yet, but certainly higher than the ones I've just discussed, that might also be present. And so in order to be able to compute accurately what's going on here, so as I said, it's a blessing and a curse, because I tried to advocate in the first lecture the fact that you do have a sensitivity to higher energies through the loops, through quantum effects, through suppressed processes in the standard model in principle. The fact that CP violation is only given by a single parameter in the standard model. So all this means that it's interesting to have this sensitivity to higher scales, but then if you want to do computations, you have to make some kind of ordered discussion of the various scales in order to be able to understand what's going on, and especially to be able to separate the part that clearly requires a specific treatment that goes beyond the perturbative treatment, mainly the strong interaction in the low energy part. So the answer to that is to use the fact that the scales are very much separated in order to separate the scales to simplify the problem. So it's typically what you would have. So it's similar to what you have for the Fermi theory for weak interactions. But since we know already at the time of Fermi, obviously you didn't know the full answer. So you had to first construct some kind of theory that had some difficulties or problems, but which is perfectly fine at low energies. And then when you increase in energy, you understand better why this description at low energy is valid. So now I'm just reversing the argument and just telling you, we know already the answer concerning, for instance, imagine that you want to describe the interaction between 4 quark through the W. And so you would say, okay, so this is a typical interaction that I can have between 4 quarks, and then when I'm looking at low energies, at the typical, I don't need to know all the details of what's going on inside. If I'm looking at a state that contains, for instance, a B quark decaying into these 4 quarks, I don't need that, because actually the W is so massive that I don't care whether it's propagating or not. On the time scales I'm interested in, finally, it's not. So I can just describe everything through a contact interaction between 4 different quarks. So here I've chosen randomly the 4 quarks. So it's just in order to get something that is simple to discuss afterwards. Okay, so that's going on at low energies. And so the simplification that you do actually, so if you start from the expression that you had for it's not the full answer, but it's something that is simplified enough for what I want to discuss here. So here would be the amplitude that you have coming from the electroweak theory of the standard model. And then what you say is that at low energies, I can just neglect the propagation, meaning that the momentum of the W is never going to be very important compared to its mass. And so in the end, what I have for the low energy theory is something which will be just the product of 2 different kinds of terms. One part, which is a pure number, so there is nothing propagating anymore. It's just a product of various terms that actually correspond to the remain of the short distance physics. You see that it has some memory of the fact that it came from a W. You've got the CK matrix that is coming from the W interaction. You've got the Fermi constant, which is a combination of the coupling constant of the W and the mass and its mass. So all that is giving you something which has some memory of what's going on at short distances, but it's a number. And then you've got a 4 quark operator made of the light fields. And then this operator that is higher order compared to its dimension 6 operator. So that's something that wouldn't be present in the standard model, but in low energy theory it is. And when you start discussing, for instance, the fact that B decays into some kind of final state, whatever it is, then you would have this coefficient, which is short distance, the Wilson coefficient, multiplied by a matrix element between the operator that you just obtained and the long distance. So it's a matrix element that actually encodes long distance physics. And so by doing so and determining, so here it's done in a very crude way, but you can see that you will have some kind of separation scale between the two, determining the part that goes into the long distance term and the part that goes into the short distances. And actually that, well, obviously you can do that in a more abstract and more proper way by just saying that you integrate out the degrees of freedom that correspond. So in your, if you think in terms of the functional integral, you integrate out the degrees of freedom corresponding to massive or energetic modes. So that means that, for instance, you're going to obviously to have the T, the W, the Z, the X being integrated out, but you do have also other modes. For instance, energetic gluons or photons could be taken into those Wilson coefficients. Whereas you will find the operator being built only from long distance, well, low energy modes. So the last thing I wanted to advertise in those general comments is that here, so we know already the answer. We know that what is the underlying theory. Now, if you reverse once again the idea and the process, imagine that you don't know anything about your underlying theory, but you know that in the end your experimental data are well described by this kind of structure at the level of the effective theory. Okay, you don't know what's the reason for the value of the numerical coefficient that you have in front, but you do have the idea that you do know that it carries some mass, because actually it's multiplying a dimension 6 operator, so it's related to it has a mass dimension. So and actually the mass dimension corresponds to the scale, more or less, at which you have this short distance physics occurring. So the value of the Wilson coefficient is going to tell you something in principle about the typical scale at which the physics that you want to probe is occurring. Obviously, that's modulated by here you see that GF is G squared over MW squared. So that's related to the mass of the W, but it's modulated by the value of the coupling constant. So you don't have full information about this, but at least a part of the information. The second thing is also that even though you've got an operator that already is telling you quite a lot about the structure of the interaction. So here, even if you didn't know anything about the standard model, you would say, oh, well, look, here you do have something which involves only left-handed quarks, and that has a gamma mu matrix. So probably if I play the game of trying to find a mediator for this, I would probably try to find something which is a spin-one object, coupling only to left correlates. And so that would bring you naturally to the right direction in order to discuss what would be the underlying physics. So you can see just what I just wanted to say here, that you can see it both ways. You can see it as just this effective Hamiltonian aspect. You can see it just as a convenient tool to organize the discussion of the computation within the standard model, and I'm going to go there. But you can also say, well, if I look at the standard model and I take the low energy description and then I add some effective operators to this, and I try to determine the value of the Wilson coefficients associated to these effective operators from the data, then knowing that some operators seem to explain the data might help me in order to determine the underlying physics. It's only a partial information, but it is an information. Okay, so just to go on a bit more in detail concerning a very simple example of computation within this effective Hamiltonian approach. So, and I think that's useful in order to get an idea of why people are so interested in using this technique, even though I've already advertised. Okay, so we still keep with this 4-quark operator that I had before. But then you say, okay, so since I've heavily advertised the problem posed by the QCD effects, one may wonder what is the impact of QCD corrections. And so that's generally what you can think of, is just to have gluons being exchanged between two of the four quarks. And so that means that actually, because of this exchange of gluon, you will have, in general, at the level of your operators, the possibility to change the colors of your various external legs. So in the end, that means that what you will have for your effective Hamiltonian is something that will involve very certainly, and actually when you do the computation, you can check that's the case. I'm not very, it seems, wait a minute. I can see there's not answering anymore. Here it is. Okay, very good. Okay, so you will have, in general, two different operators. So one, which is just the one that we had before. And so I'm just writing it this way. So where I've got typically V minus A. That's going to be to keep track of the fact that I've got left-handed here. And then alpha and beta are color indices. But then, as I said, I can also have, and I will have, a contribution that has a different structure here. And actually, you can play with Hertz identities and the properties of the SU3 group in order to recast this in terms of operators that have a Q bar, TA, Q, or this kind of things, Q prime, in order to get a structure where you have in the bilinear only the color indices, given color indices, and no cross terms. But this way of writing is also possible. There is no problem with that. Okay, and so this was already given at leading order before corrections, and then that's a new term. Okay, so in the absence of QCD, you would have just what we discussed before, the fact that only one operator is present. And then the question is, how does it change with QCD corrections? It seems that I'm not very okay. Okay, and so if I want to do that, so in principle, the idea is that these coefficients are short distance contributions. So that means that in principle, if at least the separation we make between short and long distances with this scale, intermediate scale that we've not really discussed yet, mu, is relevant, then in principle we can consider any convenient external state to make a computation in order to determine the value of this Wilson coefficient. So obviously, we can, in particular, take free quarks. That's going to be what we're taking with. So neglecting the masses, and assuming that they are of shell by some quantity, which is going to be a p squared. Why do we do that? It's just that this way, we don't have to bother with the quark masses in the computations we're going to make, and that's important because that's going to make the evaluation that I'm not going to discuss in detail. I'm just going to give you the results, but the evaluation is going to be much easier. But when we're doing that, well, yes, I'm sorry, Tim. I will do my best, but okay, I will try to be a bit clearer. I will probably write a bit larger then. Okay, so why do we want to do that? To have this off-shellness present? It's because since we have neglected the masses, in principle, we would have infrared divergences to deal with, and one way of avoiding this infrared or to keep track of this question of infrared divergences is to have an off-shellness of the masses to be of the external quarks to be implied. Okay, so now if I'm just looking at the expression that I will get if I try just to compute within the standard model all the gluons here. So I remind you. So if I'm doing the computation in the standard model and I do the computation of all these corrections, what I will get for the amplitudes so you do have a term that corresponds to the leading order, and then you have corrections that are present. So one term which is proportional to the initial matrix element, and one which actually has the color indices swapped. So this is just the evaluation. So M1 and M2 are matrix elements which correspond to the leading order evaluation. Where here, what I mean here are not fields, but these are not the fields. Here it's really, but the solutions to the Dirac equations. So these are spinors. So actually, I should have written something like U bar index B and VC index C and so on, just to tell you that these are the spinors. And so this M1 and M2 are actually number evaluation of the operators, with taking into account the fact that you're sandwiching these operators between external states made of free quarks. So the structure is this one. So you do have two contributions from the gluons, one corresponding to just the same structure as the initial one, and then, so here at the first line, and then you got a structure that swaps the indices. So that's, for the moment, we've done nothing. We've just computed in the standard model. Now the question is, what's going on when you're considering the effective Hamiltonian? And so in the effective Hamiltonian, then you can compute similarly. So you can compute what would happen if you just consider the operator Q2 sandwiched between the two, between the external states made of quarks. And then you have corrections to this that are very, very similar, obviously, to what you have in the standard model. Because once again, before you start having the external state interacting through the 4-quark operator, they can still emit and absorb gluons and have therefore corrections to the initial evaluation due to these additive corrections. And so if you look at this, so one thing is that you can just compute exactly like before, and you can do the computation both for Q2, so the operator that we were interested initially, but you can also do that in the case of Q1, and you can look at the result. And so if you do that, you will see that, not surprisingly, you get expressions that are first just what you would expect from the naive analysis we did at leading order. So just that if you start with the Q1 operator and you put external states, you get just exactly the matrix element, corresponding matrix element, but then you've got corrections coming from that. And actually the structure here is very similar for both operator, alpha s, sorry, alpha s over 4 pi. So something that I've not discussed for the moment. So here you see that you've got this 1 over epsilon. That's because all the expressions I've just written correspond to actually to expressions done in dimensional regularization. So typically using the MS bar scheme in order to get rid of divergences. And the point is that here you see that you've got additional divergences. You got additional divergences compared to the standard model expression. So that's not a surprise. I mean, the standard model is something that we know is renormalizable, and here we're considering a theory which is not renormalizable. And actually, the fact that we've opened we were able to express at higher energies a theory that has no higher dimensional operators was a key in order to get something which is renormalizable. So it's not a surprise that here, when I'm doing the computation, this kind of computation using 4-quark operators and looking at the structure at one loop, I do have divergences that I cannot get rid of when I try to, once I've applied all the renormalizations that were needed at the level of the coupling constants and so on. So the point is that, so that's one point. The second point is that you see that contrary to what you had before, and once again, it's not a surprise, you've got only low scales involved in the logs. So we've got this p squared, which is just an infrared regulator. And then you've got mu squared, which is, in our mind, at least, the separation between what we have at low and high energies. Whereas when you're comparing, you have, when you consider the standard model, you had logarithms running from p squared up to mw squared. And so before we start discussing a bit the implication of these additional divergences, so this is going to be a question related to RGE, and this question is going to be related to the matching. And so I'm going to start with the matching. So I'm just forgetting for the moment the presence of this extra poles that are present and that are the signs of untreated, for the moment, divergences. I'm just focusing on the matching part, so I'm assuming that I can deal with them. And then I'm just asking, okay, let's assume I know how to deal with those 1/epsilon. What is the outcome of the comparison between the two? Well, it means that if I want to be able to identify the results of the high energy theory, which is the standard model, and the low energy theory, which is this effective Hamiltonian. Well, I have to tune the values of the Wilson coefficients, and that's matching. And so I want to have the fact that I'm not really, yes, it's answering now. And so if you want to have the equality between the two, then you say, okay, I've computed my amplitude in the full theory, and then I want this to be identical to what are my expectations in the effective theory. And so if once again, if I'm not considering for the moment the issue of normalization, that means that actually I know I have to take the Wilson coefficients in order to contribute, in order to add to the contribution that you have here, present here, the contribution needed in order to get the contributions that you got there. And so when you do this identification, you get the fact that get expressions of this type. So values so this is up to higher order terms. And you see that you've got exactly what you expected, meaning that there's no real surprise, but that means that what we're saying is working. It means that we had a contribution in the standard model that was some kind of glue-on loop that would give you something that would diverge logarithmically and integrating from -p squared to mw squared. And then you broke it down into two contributions. One which is related to the Wilson coefficients, and one which is related to the matrix element of the operator. And actually, so here we did this computation using an external state that we manage. Afterwards, we can forget about this and just use this short distance Wilson coefficient for any kind of matrix element that we're interested in. Now, obviously, at some point, what we're going to say is just to consider not external free quarks, but actual hadrons, bound states of these quarks. And in that case, obviously, the question of the matrix element is going to be much more difficult. But the computation that we had for the Wilson coefficients is still valid. And here we have explicitly seen, so it's a very simple example, that we can indeed do this factorization, this separation. You could imagine a situation where you cannot do this separation for some reasons, because of the scales involved, because of the complexity of the process, I don't know. And that would mean that you cannot perform this, and then that you have to be more careful in your separation of scales. But here it works very well. Okay, the second thing that you have, so typically you would say the typical scale here is alpha s at mu. And so you see that, so this, as I said, can be reused for even considering other external states, so hadrons. But the other point that you can see here is that you do have interesting structures in your Wilson coefficients. And so typically, this is going to be interesting and at the same time potentially problematic. If you have mu of the order of MW, it's small, so no problem. But then the question is that in the end, what you want to do is to have this separation between high and low scale, certainly not at the level of the effect of the electroic theory, electroic scale, but down to the typical scale of your quark masses of interest. So typically the big quark mass, the charm quark, or these kind of things. And so if you are at the scale where this smaller, then you see that alpha s is becoming bigger, but also the log is also becoming bigger. So in principle, you might start having troubles with this large logs. And so doing just the matching this way and nothing else, you might have troubles at some point, because depending on the coefficient in front of your alpha s times log of mw squared over mu squared, you might, if it's a bit big and if mu is a bit too small, then you might have questions about whether this is a very nicely convergent expansion, and a nicely convergent way of doing the computation. And so then here, so they are potentially problematic at low scale mu. So in order to deal with that, actually, one way of doing it is just to come back to the question that I've just hidden under the carpet before, which is just the question of the renormalization. I have additional singularities in my effective theory, and so I have to tackle them. And so I'm just giving you very briefly the renormalization procedure in a simplified way, but the idea is that you just consider the matrix elements that we've just computed with the one loop corrections. And then you say that you want to absorb their singularities, their poles, with a renormalization factor. So it's you can just read off from the previous expression what they are. So you have 3 over n NC on the diagonal, because you saw that M2 is connected to alpha S over 4 pi 3 over NC and this 1 over epsilon. And then you've got minus 3s on the off diagonal. Once again, that's related to the equations that you have between the relations that you have concerning the structure functions of your SU3 group. And then, so you see that actually it's much simpler to invoke terms that will have, so to diagonalizing this this structure, which is not very difficult. You see that if you're defining this combinations of Q1 and Q2, actually the operator becomes much simpler. You've got something which is just this time are just numbers, so it's a diagonal. You don't have any crossfit between the two operators, and then you can, in a similar way, say that you use the same factor to normalize the Wilson coefficient. And then you say that you want to have you re-express, so you could write this either unrenormalized pair or renormalized, so it can be written in both cases. And now you see that because you have defined also your renormalized Wilson coefficients, you can determine then the way they're going to vary, those renormalized Wilson coefficients, they were going to vary with mu. And so that's the other part that can be done from the expression. So since you've got this relation here, which involve alpha S, and you know the value, the dependence of alpha S on mu, then you can say that you can then very simply obtain the dependence on mu. And so write a randomization group equation for both coefficients of Q plus and Q minus, so the sum and difference of the two operators. So and so since we have this the dependence on the logarithm of mu of C plus minus, then we can integrate quite easily this expression. So I just give you the result because it's not very interesting to have the intermediate steps, but that's the usual approach in order to solve this kind of differential equation. So gamma plus minus 0 is just the coefficient that you have here, and that stems from the RGE. And then you've got beta 0, which is related to the dependence on mu of alpha S. And so that's just a combination of the number of colors and flavors that are, well, the flavor active flavors of the theory. So that means that now you've got an expression, so you can recast as the value, you can compute with this the value of C1 and C2 at any scale. And so, well, in practice, just to make it plain, you've got So this is just by putting the values of gamma plus minus 0 inside and using the fact that C plus minus at MW is 1 plus order alpha S. And that's exactly what we had before, remember. We had C2, which was 1, and C1, which was 0. So when you take the plus or the minus combination of C2 and C1, then you obtain 1 in both cases. And so that's why you got, it's multiplied by 1 corresponding to C plus minus at MW. And when we do that, actually, what we've achieved this way is just to solve, quote unquote, the problem of the large logarithms. Because when you look at what you have alpha S of MW over alpha S of mu inside this exponentiated to some power. And then you can just re-express that if you wish at just this expression in terms of alpha S mu. And so you see that actually we somehow this alpha S MW over alpha S mu is just a sum of all logs of the form alpha S of n log to the n MW mu squared. So by doing this consideration of the RGE and solving the RGE, actually we've been able to sum along the way all the Wilson coefficients that all the contributions that corresponds to leading logarithms. So these terms actually they so you can do the same thing, and don't worry, I'm not going to do that here. But you can imagine of doing that at higher orders and higher orders of perturbation theory. And when we going to higher orders in RGE, you can resum next to leading logs and so on. So these one are going to be alpha S mu log n minus 1. So potentially less dangerous, but still, and so on and so forth. So next to leading log, you've got 2 of a difference between the alpha S and the logs and so on. And the point is that this way you have resummed the effects of whole series of gluon exchanges that can give you perturbatively a large contribution. So that's already an interesting achievement, especially with the idea that we wanted to separate the scales, but keep track correctly of the physics going on from the high scale down to the low scale, keeping the relevant, including numerically relevant contributions. So that's done this way, and by doing this this trick of considering this RG, we've been able to resum properly those contributions. So now what we have after applying this, so for this effective Hamiltonian, so by doing this matching and RGE, we have a way of computing the short distance part. I'm not saying that it's easy. I'm saying it's structurable, which is a very different statement. And actually, it's very challenging to go to higher orders in order to determine very precisely the values of these Wilson coefficients. But the technology needed has been developed over the years, and so it's possible to do it. And then the point is that now you remain with matrix elements of higher dimension operators involving only so light degrees of freedom, and especially gluons in the non-perturbative regime, even though obviously talking about gluons in this case is a bit of a stretch, but at least you get the idea. One last thing that maybe I can mention, so before moving to the next part, is that obviously you can apply, so the effective Hamiltonian that you construct is built to describe the interactions for given ingoing and outgoing states. What I mean by that is that obviously here I've just built very quickly the Hamiltonian, where, for instance, I would be interested in studying a B quark decaying into a charm quark and a U quark and a down quark, and you put the bars everywhere where you need them. But obviously, this is not, that would not answer questions about other kinds of physics. If I were just interested in the physics of kaon state involving only very low light quarks, this wouldn't be the Hamiltonian I have to look at. And obviously, depending on the process that you want to look at and simplify by separating the short distances and large distances of the problem, then you might have some more complicated structures than just having the situation that we had where you just shrink everything to a point. So just to illustrate that, so and sometimes it's more complicated than just one or two 4-quark operators. Just to illustrate that, coming back to an old friend now that we already discussed, well, actually a slight change. So B2S transitions, so we discussed that when we were discussing flavor changing neutral currents last time. And so just for fun, I'm just considering the fact that the photon is not real, or the Z is and is converted into L plus L minus, so lepton, E plus E minus, mu plus mu minus, tau plus tau minus, if you wish. And then, as we said, we've got U, C, and T running through the loop. You've got a W. And now, if you think, so this is something that certainly, because of what I said concerning flavor changing neutral currents, is in principle interesting to discuss in these terms. You want to separate really what's happening at short distances and long distances, because you've got at least some kind of idea that that might be a hunch, that might be maybe this could be sensitive to new physics. So you really want to separate what's going on. But actually, when you think in terms of the operators that you can have to consider when you start dealing with this, the effective field theory, then it starts being quite complicated. For instance, if you say that you have a top and a Z, then clearly you don't wonder, you have to consider that everything is integrated out, and then you get really operators that will be similar to what we had before. So this time it's not 4 quarks, 2 quark, 2 leptons, but it's still 4 fermion operators. So typically that will be things looking like, I don't know. Sorry. So generally you would expect to have still a remainder of the fact that it was a W exchange, so that you got the left-handed part contributing for the quark part, but then you could imagine to have either an axial or vector coupling to your leptons. But you can also imagine the situation where it's a photon, and then the photon will propagate. It's still a light degree of freedom. So this time you will have something like, a reason I can discuss later, will be more of this type. So you do have to consider an operator here. But then that's not the full story. It's not just the operator. You have still, so the emission of a photon that will propagate, and you have to take into this propagation. And within the effective theory, you still have the interaction between a photon and a lepton pair. And so you have to consider that. And you can even do something worse, that you say, okay, but I could have a photon and then an up quark or a charm quark, and the up quark and the charm quark are still degrees of freedom propagating in my effective theory. So another thing that could happen is just that I've got B and S with here an operator which will be actually O2, which will be just the operator we discussed before, because that's going to be O1 and O2, because these are just the W exchange between the various quarks inside. And then you close the loop and L plus and minus. And so that means that here you will have something which is even worse, or at least even less simple, because here you see that you have to take into account not only a short distance part, but also a long distance part, which is made of the propagation of a quark loop, then a photon, and then the decay into L plus L minus. So once again, that was just to advertise the fact that the very simple discussion I had before might be relevant, and we will see that it is relevant in some cases, very much relevant in some cases, but it can very quickly become a bit more complicated, still within the framework of the effective Hamiltonian, which is useful because you have already separated part of the electroweak effects into Wilson coefficients, but still that doesn't mean that everything shrinks to a point, which might be something that you might have the feeling after hearing my discussion. Okay, so I've already spoken for 1 hour. Maybe I can suggest that we make a short pause for 10 minutes. All right, so after this discussion of separating short and long distances and discussing a bit in more detail how you can actually determine the short distance part of your theory. So we've got rid of all the electroweak part, we've got rid of the gluon of high energies because we've resummed them into the Wilson coefficients. Then we remain with, well, I wouldn't say the most difficult part because the rest is not easy. It's really not easy, and it can be very challenging at times. But a part which is also very complicated, and which is everything related to the hadronic matrix elements. Okay, so the thing is that we are going to, so in general, what you have is something which will be a final state, an operator. Sometimes, as I already showed you, that's not just that. You can have also things where you have still to take into account the propagation of additional light degrees of freedom. So, but at the very least, if nothing else, you have necessarily to just consider the situation where you've got the decay of hadrons, whatever it is, I put B, but that could be anything, going for an operator, and then in a final state. So at least to consider. So as I said, see before the case where you have also to take into account contributions from the propagation of light degrees of freedom. Okay, and so now the question is what kind of final states we can hope to tackle, not in a too difficult, well, being reasonably difficult, but not too difficult to analyze. And so the idea is that so the matrix element is easier to tackle if there are not too many hadrons involved. Intuitively and in practice, naturally, you can expect that if you have too many hadrons in your final state, they will interact with each other, with your initial stage, through the interaction, through long distance, strong interaction, and that's going to be a hell to describe and to understand. So probably if you keep to a light, a very small number of hadrons in the final state is probably better. You might think that it's not very ambitious, but it's probably better to try to do physics with processes that you control quite well at the theory level. Why is it so? It's because, once again, you have the idea that you want to discuss properties of the physics at high energy through processes occurring at low energies. So through the running, we see that there is only a small limited sensitivity to these high energy processes. And so you need to have a good handle and a high accuracy when you want to extract information from what's going on at the low energy scale. So this is because you want to do precision physics. And if possible, not too much model dependence, even though there is some needed in order to tackle this part. Okay, so that means that actually we're going to look at things where the decay is generally into no hadrons, one hadron. I'm not going even to discuss two hadrons here. It's already quite difficult. So the first version, and that's quite an easy thing, is the leptonic decay of a hadron. So that's probably the simplest version of the problem you can imagine. So I could take whatever I want. Okay, let's take D minus, so a charm meson decaying into a muon and a neutrino. And so what you have is, so in the standard model, what you have is just a D minus that contains a C bar and D, and then a W minus, and then going into a mu and an high neutrino. And then if you, so obviously that's a bit of a hammer to kill a fly, but you can say, okay, I can just compute that in the standard model. I could also think in terms of my effective theory, and what I have is just then a 4-quark operator, a 4-fermion operator, sorry, not 4-quark, that is present here. And actually what you see is that here the separation that you want to do between the various degrees of freedom is quite easily achieved if you just neglect the electromagnetic interactions. If you do neglect the electromagnetic interactions, then here you've got the strong interaction part. And then here you've got something which is purely related to, which in principle would have electroweak interactions, but which is a free if we neglect. Okay, here we are. If we neglect electromagnetic interaction. And so actually you can see that at the level of, so imagine that you do your computation inside your effective theory. Then you would have something which is something proportional to GFVCD, and then you would have something which is, so here I'm a bit more careful concerning my notations. So here that's the free Dirac solutions. So these are the spinors, and then you've got a remainder. So the four quark operator, the four fermion, sorry, operator can be separated into two bilinear. One of them is just related to what's going on the left-hand side, and then that's something that can be treated immediately using the solution of the free Dirac equation. And then you've got a term which still involves fields, the quark fields, and that will be just involving, so a hadronic matrix element. Okay, and the point here is that this guy in principle, that's really a non-perturbative QCD, so you don't have a clear way of computing that from first principle immediately. But the thing that you can say that you do have the invariance of the P invariance of the strong interaction that means that actually you've got only the actual component that is to take into account. And then the fact is that you've got this matrix element that is by Lorentz as a single Lorentz index, and which is actually depending on a single kinematic quantity, which is the momentum of the D. There is nothing else. So you can say that it must be proportional to the momentum of the D, and then it's proportional with a proportionality constant that is called the decay constant of the D meson. And so you don't know what it is from first principles, well, at least in a naive way. But at least you know that this will involve the whole part that is hard to tackle, which is related to QCD. And so you can just compute easily the branching ratio. So here you've got the decay constant. And here you've got the fact that it's proportional to the lepton mass. So that's the so-called helicity suppression. That comes from the fact that essentially, if you consider the limit where the mass of your lepton is 0, then you have a problem because angular momentum conservation would require you to have the same helicity for both leptons, yes, going out of the decay, but then the weak interaction, the structure of the weak interaction would require you to have opposite helicities. So that means that in this limit, the decay is forbidden. So obviously the way out is say, oh, but you have to take into account the effects of the lepton masses, and that will then allow you to have a mixture and a difference between what is helicity and chirality in the discussion. And then that explains why you have something proportional to the mass of the muon in the game for this branching ratio. So this is true up to electromagnetic corrections. Okay, so now moving to a more complicated situation. We move from the situation where we have only a single, when we have a hadron decaying electronically, so we didn't have any hadron in the final state. And then now we move to the situation where, once again, we have one meson, let's say this time the G0, decaying into a pion and a lepton pair. Okay, and so once again, R. And so you can, once again, we could analyze, if we wish, in the same way in terms of the effective Hamiltonian. So for fermion operator, once again, so the story goes exactly in the same way. So I'm not going to repeat the intermediate state, but so the decay amplitude can be expressed in terms of a single unknown quantity, and that's the matrix element for the same reason. And so here, once again, because of the parity of parity conservation of strong interactions and the fact that you've got states with definite parities, this time you can, and these are pseudo-scalar states, so that means that you get a -1 each time when you are considering the parity properties. That means that this time it's only the vector part of the current that is actually contributing. So fair enough. But then we can play the same trick of decomposing according to the Lorentz structures because of Lorentz invariance. But this time we've got two different quantities, two momenta to consider. So we can build up two different objects. So customarily, but that's so you've got a term which is proportional to the sum of the momenta, a quantity which is proportional to the difference of the momenta that corresponds actually to the momentum of the lepton pair. And the point is that this time we did, so here in principle, F plus and F0 are quantities that can involve any kind of scalar quantity that you can make out of the kinematics. The point is that if you think of it, you've got it corresponds to products of two momenta, but PD squared and P pi squared correspond to the masses. So these ones are not actually quantity, they are fixed quantities, but the fact is that the product of the two PD times P pi is not. And so you can actually consider that there are functions of Q squared, which is exactly the same thing because you can find the product of PD and P pi inside Q squared plus M pi squared and MD squared. So just before, for the decay constants, we didn't have this problem because there was a single quantity that was a kinematic quantity, the momentum, Fd, if the decay constant, if it had to depend on something, would have to depend on the single scalar that you could build, which was Pd squared, and so that empty squared, so there is no dependence. Here, on the other hand, for the two quantity F plus and F0, which are from so-called form factors, obtained from the Lorentz decomposition of the matrix element, are functions of Q squared. Okay, so obviously, if we start playing with, and I'll come back to that later. So this decomposition in form factors depends on the quantum numbers of the current and the external hadrons. So you can, if you want to play a bit, you can think of what would happen if, for instance, it was not a vector or an actual current, but a scalar or pseudoscalar operator. If you have a meson that is a spin one object, so there is a new degree of freedom which would correspond to the polarization vector. So you have new Lorentz structures to play with. You can even start thinking what would happen if we were considering baryons, and that starts being a bit more tricky. How you handle the fact that you've got half spin quantities to consider. So that you see that actually the number of form factors and the structure depends very much on those quantum numbers, both at the level of the current and at the level of the external states. Coming back just to the structure, so just to show that in the end, once we know these form factors, we know everything we have to know, at least for this kind of sorry, 24. I didn't write the correct one. So you do have, as expected, terms that will correspond to the phase space. And then you will have terms that will be proportional to the various form factors with kinematic factors in front. I'm just writing that for sake of the demonstration. Okay, so that's telling you that, at least in simple case, once again, I already warned you that in some cases you cannot just reduce everything to form factors, but at least you do have a contribution from form factors, whatever happens. Then once you have this non-perturbative information that you derive from your separation of high and low scales, then you are able to compute these the decay rates and other quantities that can be of interest. I show the decay rates, but you can also think of the geometry, build angular observables. I'll come back later to that. But so since those form factors are quite important objects, so what do we know about these form factors? Well, not as much as we would like, probably, at least from general principles. So one thing that can be obtained is, in generality, is that there are some aspects of the analytic structure of the form factors that can be obtained on general grounds. So exactly like when you do have in general a correlator, it contains a lot of information, and actually in the end, what you're using for practical computation of decay rates is only a very limited part of this information. You have to use the LSZ formula in order to project the information that is contained inside this correlator down to very specific states. As an analogy, it's not the same thing, but as an analogy, you do have information on the form factors that it goes beyond what you have just for what you need just for the computation of a given process. And so the main element for the discussion is when you're discussing, so you have the use of the unitarity of the S matrix that you can exploit in order to get some limited information about what you expect for this form factor. So you've got this construct that is just the overlap between an in state and an out state, and you can identify in that the part corresponding to the transition matrix. And so when you want to actually compute the transition probability amplitude for a given process to occur, multiply by I alpha b. That's actually contained inside the transition amplitude. Obviously, the identity part of the scattering matrix is just telling you that you have an overlap between states that do not interact, remain the same. And then, since you have the fact that your S matrix is unitary, that has a consequence for the T matrix. And actually, when you write down that for your decay amplitudes, you do see that you do have a relation between discontinuities or imaginary parts of your amplitudes. So when you go from a state A to a state B, and then you look at the presence of an imaginary part, that's related to the possibility to go through a real state in between. And so that means that at the level of the form factors, because the form factors are derived from those kinds of decay transition amplitudes, then that means that actually the form factors acquire an imaginary part when you can insert real intermediate states in between the initial and the final state. And the fact that they're real, that will be dependent on Q square, because that corresponds to the regime, the kinematic regime where you are. So just to make that maybe a bit less obscure, if I come back to my d2 pi L nu form factors, so I started with a discussion where I had this transition between a d and a pi. And if I'm looking at the value, so the kinematic values that are of interest for me when I'm looking at that, that would be for q squared, that will denote t here, between ml squared and md minus m pi squared. But actually, I can think of looking at this vertex exactly like in a more fundamental theory. I have the same vertex whether I'm looking at incoming or outgoing states. Here I can do that also at the level at which I'm looking at the external states for my, my hadronic theory. And then if I look at what's going on with exactly the same vertex here and d pi, that would correspond to the situation where I'm assuming I'm looking at the same vertex, but this time with d pi in the outgoing stage. And the point is that this will be possible for md plus m pi squared. So above the threshold, the d pi threshold. And actually here, so before I couldn't put any kind of intermediate state no matter what. So that means that here f, my form factor is real, but here I will have an imaginary part. Why is it so? It's because I can imagine of having, for instance, a rescattering like this. And if q squared is larger than d pi, then obviously I can go through an intermediate state, which is d pi. And if I even increase in q squared at some point, I can even go above other thresholds, for instance, dsk, which is also possible. And then I will have, I will have here an additional cut. So I start having a cut for this this first possibility of an intermediate state contributing to the imaginary part, and then when q squared increases, I will have additional cuts coming from higher, more massive intermediate states. And so the point is that this analytic structure is actually the structure that you will have in general from form factors with a simple analytic structure. So you have poles for narrow resonances, cuts along the real axis when new channels open, but then analytic everywhere else. And when I mean that, I mean by when I'm considering the complex plane. So I remind you, if t is q squared, I get something, a structure would be very simple. So a cut, actually several cuts. The first one being the d pi production. Larger, corresponding to t plus that I've just written before. And then here, I will have to write it. Okay, I will try to use color for once. So that would be the cuts here, so the non-analytic structures. And then when I'm looking now at the physical range, that's going to be here. So coming from ml squared to t minus and t plus, as I said. And that's it. Well, that's it up to the fact that if you wish, you would have, for instance, resonances. So for instance, you've got a D star, which is just close, very close to the d pi threshold. So you could consider it as being either an effect of the opening of the d pi threshold or an actual full-fledged resonance. You could imagine that. So the thing is that in any case, you see that actually the structure of the form factors is very simple, but it's connecting very different dynamics, as could be expected. So there is quite, even with these simple elements, there is already quite a lot of physical information included in this. So one can make some use of this. So the first one is that, and that will be used in, I will refer to that in some instances when we're discussing CKM properties, CKM determination. So the fact is that you see that you've got this structure, which is a cut plane. And so when you think of trying to determine information about those form factors, you can try to compute for in some kinematic range, or measure in some kinematic range. You can also imagine that. And then you try to do the extrapolation of this into a different regime. And the question is that the fact is that it's very nice to have this analytic structure that you have, but it's not necessarily the easiest structure to make extrapolation. For instance, imagine that you have some information in the physical range, and then you want to extend that. You know that the radius of convergence of the series you're doing, for instance, to do your extrapolation, will be limited because you've got the cut in T plus you're going to hit. So you cannot imagine, for instance, extending this representation above the cut, even though you know that actually the structure is very simple. You've got the cut, but above and below, this is analytic. And so that has led to quite often to propose an alternative mapping to describe this, and that's actually which is called Z expansion. So typically what you will say that you will just build a quantity which is this one, where T0 is arbitrary. It can be tuned for based on various physics consideration. But the point is that this Z definition of Z actually will, will actually lead to the a mapping of the plane. So the plane in T is mapped into a disk of radius 1, and the cut on the right hand is actually pushed at the circumference. So and so now you've got you can imagine doing writing a series in Z with better convergence property than in T, just because you're not going to hit the cut in the same way. Actually, you can hope to map the whole plane inside, and then just the circumference would just be the problematic region, but it's far away from the center where you start the expansion, in order to have difficulties with the unitary cut. Okay, so that's the first thing. So this idea that you can actually, since you know something about the analytic structure, you can choose a parameterization that will help you in order to be able to do extrapolations in a better way. A second thing that you can use, and I will talk about that very briefly, just is what is called dispersion relations. So the idea is that actually, since you have this very simple analytic structure, you can imagine doing having connection between values of f in very different energy regions. So imagine that, so actually the thing is that you can use Cauchy theorem to determine the value of f for a value of t that is away from the cuts. So assume that you're in the physical region for d2 pi, for instance, and then you define a small circle of integration around this, and then you say, okay, I'm integrating over this small circle of integration fz, so the value divided by z minus t. So the point is that here you're in a region where f has no singularity, you have a pole, you're doing the integration over the contour, then you're selecting out of that your value at z equals t, so the value at t. And then the fact is that you can deform this contour, and in particular, because it's unitary everywhere apart from along the cut, and so you can imagine to deform it in order to get to follow the cut and then to have a large circle. So that's something that is quite reminiscent of things that you do when you start discussing the behavior of the propagators in quantum field theory courses. And then that means that actually this way you can relate the value of ft and the value, so this is actually related to, because you're taking the value below and above with opposite directions. So in the end, you're going to get the difference of f along the cut just above and just below. So that's going to give you in the end something that is related to the imaginary part of f, and then the value of f at very large t. So this means that actually you can relate the value of f for instance, in the physical region with an integral that will involve the value along the cut, and that is related to the potential intermediate states in that region, and the value of f at large t. And so you see that you can hope to get information in a given region by connecting it with a different region where actually you can, for instance, hope to use the fact that there is a large value of t that is flowing so that you can do an expansion using that, or you can have information, experimental information coming on the cut, coming from the fact that it knows something about possible intermediate states. So this is something that can be used in order to get a handle, a generic handle on the form factors. The last element I'm going to mention here, well, I will mention two elements still. Okay. So the last element that I wanted to advertise at this stage is that you see that you have phases that come from the strong interaction here. that we've discussed in a very particular region of the form factors. In general, when you have rescattering, two-body interactions, you will have strong phases. We discussed already weak phases coming from the electroweak part of the standard model. And so you see that their origins are very different. And so that means that also concerning CP, that's going to be very different, because the weak phases, we discussed that when we're looking at the action of CP on the currents, we see that actually we're swapping the positions of the various fields. And in the end, we have, because of hermeticity of the Lagrangian, we do have the complex conjugation for the CKM part, for instance. So the CP conjugate of a process with VCKM is going to have VCKM star to have the complex conjugation. So that means that the weak phases, they are actually odd under CP, just because of the discussion we had when we discussed CP validation in the standard model. The strong phases, they are coming just from the strong interaction, which is completely CP invariant. So if I was to consider the two-body interaction between two particles, two mesons, two hadrons, or their CP conjugate, I would get the same answer. There is no difference between the two. And so that means that the strong phases I've just discussed for the form factors, actually, they're going to be even under CP. And that's something that we're going to encounter when we discuss the CKM matrix, because actually the presence of different phases in the dynamics of the decays, some of them being strong, some of them being weak, are going to be important when we discuss CP asymmetries, so the quantities that are able to highlight CP validation. Okay, and the last point I wanted to mention is, well, two more points. The first one is a very quick one. You might think, okay, so we have already we've discussed decay constants, form factors, so why not keep on and increasing the number of hadrons? So exactly for the reason I just mentioned of the difficulty of having to deal with rescattering, it starts being complicated. So generally you stick to one incoming, one outgoing, and nothing more. And then you try to get back to this situation for all the processes you consider. That means that actually we're very limited in what we try to consider as processes. There are plenty of more complicated transitions that we will not be able to deal because we're limited in our abilities to describe or understand the strong dynamics that is at play. So that means that essentially the answer will be no if you want very accurate information. That doesn't mean that you cannot try, and that doesn't mean that sometimes the models cannot give you some information. I'm not saying that it's impossible to do more. I'm just warning that you're facing very quickly strong limitations in the accuracy of your predictions and your capacity of improving your predictions in a controllable way. So that means that actually we're going to have essentially decay constants, form factors, and also so-called back parameters. And that's something that I will discuss next time. But so we are limited with 1 hadron to 0 hadron, 1 hadron to 1 hadron, and 1 hadron to 1 hadron. The only point is that it's related to neutral meson mixing, so it's the evolution of neutral meson, it's not their decay we're considering when we're dealing with back parameters, but I'll come back to this later. And so when we try to go beyond general principle of quantum field theory for these quantities, so what can you use to compute those form factors and decay constants? So broadly speaking, you've got three possibilities. Two of them are actual computations. One is more trying to organize your lack of knowledge. So the first one is lattice QCD. So what do? You just discretize QCD. So it's a 4D grid in a box. And what you do is just you put, so you're putting a discretized version of QCD, and then you have in some points of your grid, you do put currents that will correspond to which have the quantum number of the mesons you're interested in. So for instance, you put something which has the quantum numbers in order to be related to a D meson, then you put somewhere else a current that has the quantum number in order to couple to a pion, and then you put somewhere the operator or the bilinear that is of interest for the transition. And then you do that, and the point is that at large separation, actually you're going to be dominated by the lowest states. And so that means that you select this way the D meson and the pi contributions. And so from the consideration of this correlator at large time separation, you will be able to single out the contribution that comes from the D2 pi form factor. It's the same conceptual idea as what I mentioned already concerning LSZ. You try to find a limit where actually the only contribution that will matter is the one where your currents are coupling to the state you're interested in. The difficulty is that this is a 4D grid, which is with an Euclidean matrix, so you don't put any, so there is no difference between the time and the spatial components. So that means that in particular, you don't have access to all the possibilities concerning the value of Q squared. And so that means that you don't have an easy access to rescattering. So the objects I just mentioned before, where you've got one hard one at the beginning, one at the end at most, are well suited for this kind of discussions. The second thing is that you don't want to, since you're in a box, you would like to conceptually not to have problems with, you would like to keep your state within the box in order to avoid having too important finite volume effects. And so that means that generally speaking, you would like to have transitions that keeping back, well, oscillating between Euclidean and Minkowskian way of thinking. You don't want to have a situation where you have a D that decays and then the pi and the lepton and the neutrino are flying away very quickly, because actually they're going to get out of the box very quickly and finite volume effects are going to be important. So that means that actually you would like a situation where your D decays and your pi that is emitted stays more or less in the same place or moves a bit away, but not too much. So that means that actually you prefer to have a situation when it's a large Q square taken away by the lepton pair. And so that the final meson is almost at rest. So no recoil. So that's one possibility. The second one, which is, and I'm not going to line cone, sorry. Not going to discuss that in very much detail because of lack of time. But we can discuss that later during the discussion session if you wish. It's the opposite. It's considering it's interested in the situation where you have low Q square, so the pi is emitted with a large energy. And in a nutshell, why is it interesting? Because then the pion is emitted with a large energy. That means that actually it flies almost in a light along a light direction. And that means that actually you can see its component as being almost collinear quarks. And so that means that actually you can start having a description of your, in this particular regime, using objects that will be equivalent to pattern distribution functions. They're slightly different. They're light cone distribution amplitudes. But that means that you can actually start using objects that will describe the repartition of these quarks into a meson light cone distribution amplitude, sorry. And the fact that you've got this configuration with your collinear quarks is actually allowing you to make some simplification in the evaluation. I can come back to that. The last point, and don't worry, Julia, that will be very short, is that you, and Fabio, sorry, it will be that actually, so these two tools are actually tools where you're breaking down your computing actually the form factors either directly numerically or by separating a part that can be analyzed in simpler objects that are light cone distribution amplitudes. One last possibility is to use effective theories, especially heavy quark effective theories. So what's the idea? That to say that actually when we look, for instance, at B2 pi form factors, the way I treated that for the moment is a bit to say, well, you've got the strong interaction in the non-perturbative regime, and we don't know anything. But actually, that's if you've got a heavy quark, you can still play games and say, okay, look, it's true that I've got lambda QCD. I've got my light quark that are present, but clearly MB at least is very large compared to lambda QCD. So I can still try to do some kind of expansion and to separate gluons of order lambda QCD and gluons of order MB. And those ones, I can treat them perturbatively still. These ones will go into reduced hadronic matrix elements. So it's one step further in the reduction that we already did when we have the short distances coming from the electroic theory and the long distances coming from anything below MB. We can say something a bit more subtle by saying, okay, if there is a big quark, then we can still separate and further put in the perturbative part some of the elements of the form factors and get reduced hadronic matrix elements that are really very low scale, very low energy, strong interactions. And actually, this allows to relate various form factors in terms of a subset of reduced matrix elements that will correspond to reduced soft form factors. And so the point is just that this will allow us to organize a bit better our ignorance about those form factors by saying, I don't know what they are, but more or less, these three form factors, they do correspond to one underlying soft form factors up to corrections that I can compute. I'll come back to that probably during the next lecture. Okay, I think I'm already running quite late, so thank you very much for your attention.